Do you know why the spice simulations are indispensable in the VLSI industry? Do you know what are the three different kind of spice simulator used by the VLSI industry? Do you know why the analog and digital simulations resides on the two opposite poles of the earth? Amazingly, they can be clubbed together using the mixed mode or mixed signal simulations. Want to know what are the various sectors of VLSI that uses spice today and why you should learn it? Stay tuned till the end of the video to know all the answers and more.
Hey guys, welcome back. In today's episode, we are going to discuss the below points. First, we'll go in detail of the digital versus analog simulations. So we will understand the fundamental difference here and we will segregate the things which are very much different in between the two. Next, we will talk about Verilog versus spice simulation. So this was a generic comparison and this will be a very specific comparison. In the next point, we will talk about what spice netlist is used for in VLSI. That means what are the purposes which are served by the spice in the VLSI industry. So we will point out the areas, domains and applications. Next, we will talk about the industrial spice simulator that exists in VLSI. In this series, we will learn about the spice language. The language at the baseline remains the same, but for your classroom, there will be some different simulator like pSpice. In this series, we will learn through the ngSpice, which is another spice simulator widely used by the open source community. And this is very much user friendly. And in the industry, you will find there are different categories of spice simulators. These simulators will use the spice language as the baseline, but as a software, they are much more advanced so that they are capable of handling a huge design. Next, we will talk about where spice is used in VLSI. So we will point out all the areas where the spice is used in VLSI. Next, we will talk about what are the analog mixed signal design and verification is. So this is basically the mixed mode verification and design. So generally first the design is made, obviously then it is verified, but the entire process is mixed mode. So we will talk about this mixed mode or analog mixed signal design and verification. What this? We will get the fundamental ideas. And we also point out where the spice is used here. Next, we will talk about frequent interrelation and interaction of spice. So there are many areas in the VLSI. So there are multiple file formats are used and we will point out the interaction and interrelation of spice with those particular files or file formats and many other things. Next, we will talk about the common spice syntax file extension. So we are talking about file extension because if you use a simulator A, it will have some extension. Simulator B will have some different extension. But in VLSI, there are couple of limited file extensions. Those are used. So we will make sure that you are getting familiarized with all. Generally what happens when you run pSpice as your classroom training when you are in college, right? That time you use the CIR, but there are other file extensions. Those are used in the VLSI by the industrial tools. So we will cover the whole spectrum of file extensions. So we are done with this particular slide. Let's move on and dive deep in to the theories. Now, in this, we'll talk about what is spice and what's not. Now, the word spice, whenever we talk about, first, this particular image comes to our mind, right? Spice that we everyday use in our kitchen for cooking. Now, in industry, this is not the spice. You have to understand. And this is the design that engineer is doing, right? The spice is entirely related to this particular type of operation. And now we have talked spice, generally you know this, right? And now we are saying, no, this is the thing that we actually want to use in our VLSI area. Now what is spice then? Spice is nothing but an abbreviation and that abbreviation is simulation program with integrated circuit emphasis. If you see, I have put one underline of every alphabet here. I am encircling them. So if you place them side by side. This is SPICE. So this is the full form of the abbreviation SPICE. So the SPICE is not a word, it's an abbreviation, that is Simulation Program with Integrated Circuit Emphasis. This is the meaning of the SPICE that we use day-to-day VLSI work, and it's not our day-to-day kitchen work. So we are done here. Let's move on to the next slide. Digital versus analog simulation. As I have said in the index slide, that here we will generically compare the two different simulation. Simulation is nothing but the virtual replication of the actual circuit that we do. Generally, Verilog used for digital and SPICE or Verilog A used for the analog. So here we will just generically compare the digital and analog simulation, how they are fundamentally different. We have to know this before we go the specific comparison. Here is the chart, right? So first, the digital simulation is on our left side and the analog simulation is on our right side. The first point is Kirchhoff's laws is not required. Let me rephrase. For digital simulation, we do not need the Kirchhoff's law. That is the KCL, that is Kirchhoff's current law, and KVL, that is the Kirchhoff's voltage law. These are not needed at all for the digital simulation. Now, for the analog simulation, the Kirchhoff's laws, that is the KCL and KVL that you know from your textbook in your undergraduate subject, right? So those are very, very much applicable and important. So the first point is done. So we do not need Kirchhoff's laws, that is KCL, KVL in digital, and we need it badly in the analog simulation. Now, the detection of change of the logic state of a node has occurred and propagate this change to the connected element. Such a change is called event. In simulation, any change in the digital value, right, that is termed as event. If you look carefully, the logic state of a node here we are talking about, that has occurred and propagate this change to connected elements. That means in a circuit, there will be nodes, right? Multiple nodes. In between, there will be components. If it is the digital circuit, there will be digital gates. And among that node, the data propagation will occur, right? Such change is called the event. Now, the similar thing in comparison in the analog circuit is the process, right? Iteratively solving the Kirchhoff's laws for the circuit at time steps selected to ensure the solution has converts to a stable value and that numerical approximations of integrations are sufficiently accurate. So in undergraduate level, you have learned about the very, very well-known numerical methods, right? Like bisections and all. So all those necessary numerical methods are integrated into the SPICE simulator. Rather, we say the analog simulator right now, since we have not specifically compared. So for each node, right, there will be circuit nodes in the circuit connected and there are analog components, right? So they are the Kirchhoff's laws. That means the KCL and KVL has to be solved for each of these nodes in each time step. So in digital, there are time step. In analog, there are time step. Time step is common in between the two. And each time step, the KCL, KVL has to be solved for the entire set of nodes. And we call it the matrix. The matrix, that means the node matrix. In every node, we have to calculate the value. And here the mathematics of the matrix comes into picture. Now let us go to the third point. When an event occurs, the simulator examines only those circuit elements that are affected by that event. As a result, the matrix analysis is not required in digital simulators. I was talking about the matrix method, and that is not at all needed in the digital simulation because we calculate here the 1 and 0s in the connected nodes. In between the logic gates will decide whatever value will be in the next node. But however, in the analog part, right, there the KCL, KVL has to get solved and we have to have a matrix of the entire set of nodes and those mathematical calculations have to be done at each time step. Now here, the simulator operates by solving the matrix of the equation at each time point. This matrix processing generally results in slower simulation times. So here a huge mathematical calculation through the evaluation of the numerical methods is performed, including the KCL and KVL. So it's a complex process and that's why it takes much more time than the digital simulation. So here is the fundamental difference of a digital simulation and the analog simulation. We already have a series on Verilog, right? There I have shown with the simulators how quickly a digital simulation is done. Now in this series, you will see that SPICE will run. However, we are doing with the small examples. But however, when we are talking about a design block in actual VLSI design, right? There, these blocks, the specific design blocks, when we try to simulate either by digital or by the analog. Say, these are case specific. Some will be by digital and some will be by analog. If even with the size of the design, if we compare the components, and here in the component in the digital, if we compare it using the gates, so in the digital we will have gates, and in the analog side we will have analog components. So if they are similar and comparable in size of the number and all, so you will see the digital simulation will happen in a very quick fashion, whereas the analog simulation will take some time. Now, in a nutshell, the runtime is very small, and here the runtime is very huge. Now, we also have a series on Verilog A, and we also have a marathon of that. There are multiple ways of doing the analog, and these things which are challenging in the fundamental comparison of a digital versus an analog simulation are taken care in those advanced languages like the Verilog A. And there is another language I have talked about in the Verilog A series, that is the Verilog ANS, where it will cover both the digital and the analog, right? That is the superset of Verilog D, that is the Verilog digital, and the Verilog A. Now, this is a common ground. That's why I am talking about the digital simulation versus analog simulation. So in digital, we can put Verilog D. In analog, we can put the Spice, or we can put the Verilog A. So to understand why we have done this generic comparison, so this side-by-side comparison is applicable for that wide variety of the languages. That is, we have just talked about in the last couple of minutes. So we are done here. Let us move on to the next slide. So here, now we are doing a specific comparison here. In the left-hand side, we have the Verilog simulation here, and we have Spice simulation as our analog candidate. Just to have some idea, that is the pictorial idea, we have put simple digital circuit here, and we have put a simple analog circuit here. So you can see there are logic elements here, and you can see that there are active and passive elements are there in the analog one. These two circuits are fundamentally different. Now, one we write in Verilog and another we write in Spice. Now, let me compare them side by side. The Verilog is a hardware description language, HDL, that is the abbreviated format. It is used to describe the digital circuit. Now, Spice, on the other hand, is a circuit simulation tool used to simulate analog and mixed signal circuits. This is the specific comparison between the Verilog and the Spice. Also, I'd like to emphasize that the generic comparison that we have done in the previous slide is also applicable, but here we are very much restricting our exact language to Verilog, and for the analog it is Spice. So next point is Verilog models the behavior of the circuit using logical expressions and simulates the circuit using the discrete time steps. That means time steps are discrete. That means one time step we do all the necessary things and we jump to the next time step. If you are not familiar with these things, please go ahead and watch the Verilog series that we already have in our channel. You can find it in the playlist page or playlist tab of our channel. And in the right hand side, we have Spice models the behavior of the circuit using the different equations and simulates the circuit using numerical methods in continuous time steps. Now, this is a very fundamental thing that you have to understand. In digital, the time step are discrete. That means we can jump from one time step to another like this. But in Spice, the time step is continuous. That means we have very closely spaced time step. Obviously, there will be a discretization done by the analysis, type of analysis we are doing, right? The EC, DC or the transient, right? We will come about this analysis later in this series, but there we will have some spacings that we will do. But however, internally, it is continuous. Now, you can understand that why this Spice simulation is slow, because say this is the time length t equal to t0 and t equal to t1, and for the Spice this is t equal to t0 and this is t equal to t1. We are going in the same length. However, here the number of points for the calculation, simulation, the internal part that the engine, that means the Spice engine, that have to go through more cumbersome work than the Verilog engine. So Verilog engine has very less kind of effort, whereas the Spice engine will go through the cumbersome effort that will combine the numerical methods, it will combine the KCL, KVL, nodal analysis, and all about the circuit theory that you have learned in the undergraduate level. This is the fundamental difference. Next point is Verilog simulations are very fast and efficient and are well suited for verifying digital logic design such as CPUs and memory circuits. So memory circuits, as an example, we can talk about the DRAM, SRAM, etc. Here the Verilog simulation is performed and it gives the quite well picture of the designed circuit, whereas Spice simulations are highly accurate and can capture the detailed analog behavior of the circuit such as transistor level effects for the circuit like PLL, any amplifier, any oscillator, etc. Now, let me put some lights. This particular PLL is used as the clock in any of your digital circuits, so you cannot avoid the analog even in your digital design. So PLL has to be present there, and according to the need of the digital circuit, the PLL has to be designed and it generates the clock. So these are not the two different worlds existing separately in the two different universe. Rather, these two exist in the same universe. That means our Verilog and the Spice, they exist in the same universe and they do have a exchange in between. So that is the analog mixed signal or mixed mode simulation that will come later in some slide. The next point is Verilog has its extension as Verilog A and Verilog AMS for the analog simulation I was talking about, and also we have the Verilog A series in our channel and we have the Verilog series in our channel. Now we are creating this particular Spice series, so everything I think we have covered. We do not have the Verilog AMS in our channel. However, theoretically it is very easy. Once you learn the Verilog A, you will understand the taste of Verilog AMS, because the Verilog AMS act as a binder between the Verilog and the Verilog A, and it's a superset of Verilog D and Verilog B. Whereas the Spice do not have such directions like Verilog A or the AMS, because Verilog is a family of language that contains Verilog A, Verilog B and Verilog AMS. Obviously, all of them were not developed or they were not born at the same time, but they were born due to the changing need of the VLSI over time. So first candidate is Verilog, then came the Verilog A and Verilog AMS, and the Verilog AMS is the kind of binder between Verilog A and Verilog D. And the Spice is used for electrical characterizations in the VLSI industry, will come later. So I have talked about how these two simulations, something that we can compare side by side. It's because that you should know when you are doing a mixed mode analysis that my digital part will finish up soon, but the analog part, when we are going through the mixed mode simulation, definitely will take time, and accordingly the whole simulation will have much more larger time if it is compared to the digital simulation of the entire thing. So we are done here talking about the Verilog versus Spice. Now let us move on to the next slide. Now here in this slide we'll talk about the what Spice netlist is used for. In the industry, there are several applications or several means, we can say, where the Spice language and the tool are used. So let us start. First, the analog design. Say we are doing a design, say just we have came across, right, about the PLL. So that thing is done with the Spice, first of all. And that PLL has to act as a clock in the digital design. So that is the main crux here. That means the analog design we have to do, and we have to do it accurately so that the clock is very much accurate to the design. So Spice need to be very accurate for that particular analog design. One example that you can highly relate. Apart from that, we will have different analog ICs like amplifier, oscillator, all those things we can have. So that comes through the analog design. And the analog design more specifically is very much important when we are doing the IP. So many of the IPs are analog IPs, like the DC-DC IP, right? That is the analog IP. So it is applied in your handheld power banks. So it converts one DC level to another DC level. So those IPs are used there. Spice is used there. It's a real world example I'm talking about. Next is the AC DC transient. These are the analysis type, the AC analysis type, DC and the transient. Transient means with the time, DC means it's a flat DC analysis, and AC means we have something with the frequency, right? So these things are very much needed in different type of circuit and characterizing their behavior. I'm not talking about their electrical characterization that is extracted for the VLSI. Rather than if we design a circuit, we have to see how it is functioning. So for that, we have to do this kind of analysis. Even in class books, you have learned about the transient analysis and all, right? Using the L, C and R components. So this is nothing but with time. So this is the temporal analysis. With time, how the circuit behavior changes is transient. And AC-DC are very simple. The next is the test vector. Very much important, because when you have designed a clock using your Spice, right, in the analog design stage, you have to verify its functionality. For that, you have to design a test vector. It's very much true. So for that also you have to use the Spice syntax, like you are giving a digital waveform or you may be giving a AC waveform, right? So those waveforms have to be constructed inside the Spice file using the Spice language, and this will test the target design functionality. Those are called test vectors. Now test vector will mean different in Verilog and different in Spice. However, the goal, that is the theme of the test vector, is to generate some vectors that will be pushed into the circuit, that is the device under test, and they will extract its functionality. The next point is, let me put a separate in between. Next point is measurement. Now spice is used for the measurement. Now where this measurement used? Generally you have came across the standard cell characterization, right? I am going very specific here because it will be easy to relate. And there dot measure commands are used to measure different electrical properties. It may be with time or it may be some other ways, right? So the measurement commands are used and those are the part of the spice language. So it is for the electrical characterization, and these measurements are also equally applicable for any analog IP like DC-DC IP I have just explained, or like the PLL IP that we have just talked few slides back. We have our entire episode on what is the IP. The link is provided in the description. Please go ahead and watch that in case you do not know about the IP collections that are available in VLSI. So we have done talking about the measurement. Let's see the next point. It is the waveform DB. Now, waveform DB is nothing but the graphical waveform. We have used the G wave or the GNU wave when we were simulating the Verilog, right, for getting the digital waveform. Similarly, when we are doing some analog simulations, here in this particular series, we are using the GNU plot, that is, which will directly interface with the ngSpice and give you the waveform. In VLSI world, these waveform data are dumped right into files which are called waveform database. So waveform database is nothing but, say we are having the input test vector like this, and output we will have waveform like this. So all these things have to be stored in some output file. So that output file is waveform DB. So that waveform DB has to be generated by the industrial spice simulator. So there are ways that we can generate something like that, like a raw file in ngSpice, and open that file and see those waveforms, right? The input and the output waveforms, that is the test vectors and the outcomes. So spice is used for the waveform DB. And in industry, there are complex cases, right, where the waveform DB is generated first, and then some tickle script is operating on it, or maybe a Python script is operating on it, and with some API, obviously DB file will be for a particular software, and the APIs provided by the software will be used in this Python or tickle coding. So those will help to extract data. That means the electrical characterization will not be on the fly, rather than waveform DB is first generated and then we do the extraction from those waveform DB. You cannot see here because it's industrial and I cannot show here because it's not in slide. So the concept or theory I am giving you here, and those things, why those are done, because analog simulation may take maybe 1 week or 2 weeks, right, for a big design block, and those things, those waveform DBs will be dumped. So if the analog measurements are on the fly, right, for a particular IP, it may crash in between and our characterizing data will be incomplete. So to avoid those things, first the engineer generates this waveform DB and then applies either the tickle or the Python to call the APIs and extract electrical information from this waveform DB. And this is the reason, before coming to this point, I have completed the tickle series and the Python series. So you are well equipped, in case you have learned the tickle and the Python, you are well equipped to code these extraction routines. That means you will code these extraction routines in tickle or in Python, and you will include the APIs that is provided by your industrial spice tool. Now this is a very important thing, and let me move on to the next point. So here is another raw DB. In case you run a simulator Spectre, you will come across the raw output file. So those raw files, even you can generate with the ngSpice. If I get some chance, I will show you in this series how the raw files are generated by the ngSpice. Now these raw files will also contain the input vector and the output response, right, of the circuit. So these will be multiple and these will be also multiple. So both set of data will be stored on the raw file. Raw is another extension, but we call it DB because it is a collection of the data. That's why it is database. Other things are application, right? And here we are talking about the database. So these are two output database, very much important in VLSI domain. So you must know these things. Once you get the specific industrial tools manual, you will get familiar with these things. We have touched base the spice and its important functionality in the VLSI industry in many aspects here, so that could act as a motivation for you to learn the spice language, because the industrial tools, which we'll talk about in the next slide, will at the bottom use the spice deck, and to troubleshoot that spice deck you have to learn the spice language. Without that you cannot proceed even a single time step. We're done here. Let us move on to the next slide. Industrial spice simulator in VLSI. Now here I'll give you a bird's eye view of the generic, yes, we will talk about the generic types of
industrial spice simulator. And we will not go in the specific names because each EDA company have these kind of tools. Once you go to one particular vendor, you will see their tool, and if you move from that vendor to another vendor, or you can have something in parallel also, so you will see that particular kind of spice simulator. Basically, the P-Spice or on the ng-spice is not used in the large analog block design, right, or simulation in the industry. For that, we have some industrial spice, and frankly speaking, you will have their test only and only once you enter the VLSI. Outside using the open source tool, you cannot experience them. These are proprietary tools and you have to enter the VLSI and then you can work on these tools. The first category is called the pure spice. This is something which is similar to P-Spice or ng-spice. In industry, we have like H-Spice Spectre. So these are pure spice, right? And what are the properties of the pure spice? So here is the name. First one is to solve the differential equation numerically. That we have already talked about few slides back, right? When we are comparing the analog simulation versus the digital simulation, and specifically Verilog versus the spice. Next is that accurate and versatile for various analysis types. The industrial spice has a wide variety of functionalities that will meet the need of the growing VLSI area. Now, the growing VLSI areas we will talk about in the next slide, that what are the areas that have a hunger for the spice simulations. Next, slow for large or complex circuits due to the solving equations each time. So this is very slow. We are being frank here. We are being very much specific to the things that are available. So pure spice is slow. Now this is a challenge because industry needs a faster simulator because the blocks will have millions of transistors, right? So to face that challenge, the upcoming two different kind of spice is developed by the EDA industry. So the first one is accelerated spice. Now here the trick is inside the software, not in the spice language. First of all, spice language remains the same at the base level. The software that is equipped, that means the software engineering done by the EDA vendors, that is to design this kind of beauty, that is the accelerated spice. And how it is different or how it is advanced from the pure spice here, how it is different, we are going to experience here. So the accelerated spice simulators is used hardware acceleration like FPGAs or GPUs. So nowadays we have GPUs in our desktop. Right now the computer I am using for recording has the GPU because it has to process the video. Right now the video you are watching is getting processed by the GPU, right? Hardware acceleration while using the GPU is having some more cores apart from the basic CPU cores. So that gives the speed up of the limitation that we had in the pure spice. The accelerated spice will use additional processing units like GPUs. Next, simulate much faster than spice. So this is very, very fast than spice. This is accelerated spice. Again, I am emphasizing everything is engineered as a software point of view to make this kind of software. Not in the spice language, but in the software engineering part. Next, sacrifice some accuracy for the speed. So according to the user's instruction, it will drop out some of the accuracy. Say we have a particular timeline from t equal to 0 to t equal to t1, and in between we have a particular window where our accuracy is not needed. We will give instruction that we will not need the accuracy in this particular window and be accurate in this window. So the accelerated spice will read this kind of instruction through its command and it will drop off accuracy particular to this particular window. Now, the next point is it is useful for real-time applications for large simulation like Monte Carlo. Monte Carlo is a statistical analysis process and Monte Carlo is widely used in multiple research areas, even in multiple kind of statistical evaluation. And the spice tools generally have this Monte Carlo inbuilt, that is the statistical method inbuilt, and where it is needed, it will be applied. The accelerated spice now have a much more stronger way of implementing this Monte Carlo, so that when the Monte Carlo is used, it will give huge output of the statistical simulation. So here I can give you this much of information because if you want to know more, you have to enter the VLSI industry and you have to enter the IP characterization domain, right? There you will come across this kind of industry standard tools. The next one is the fast spice. We had the pure spice software and then we done some software modifications to make it accelerated. Now there is another genre of spice tool which is called fast spice used in the VLSI industry. Now what are the characteristics of this kind of fast spice? Fast spice simulator will have use techniques like circuit partitioning and approximate models. So it is different. So here it was hardware acceleration. Even some amount of hardware acceleration can be here, but main techniques are like using partitioning and approximate models. So it will do some processing at the model level so that the things become much more faster, because the philosophy of the fast spice is different from the accelerated spice. We are talking about the philosophy here. Next, it is faster than the spice for large and complex circuits. So we have improvement over the pure spice here. Next, better at handling non-linear effect but may sacrifice accuracy. Again, to become fast, we have to trade off some of our accuracy. So that is the very important thing. You have to know this. And the next point is require more computational resources. That means it will need much more CPU cores, or it may require some more hardware requirements. We have 3 different breeds of spice in the entire VLSI industry, and they are broadly categorized into the 3. First one is called the pure spice, which is very similar to the NG spice, which we are learning here. The next one is the accelerated spice, where the software is engineered in a fashion that it can accelerate speed and it can drop off some of the accuracy. And the third one is altogether different genre, and it's called fast spice, where the algorithm inside is prepared in the way that where it will handle the spice models and the partitioning methods, etc., many things to make the simulation faster. Again, here we will also drop some of the accuracy where the accuracy is not that much needed. Obviously, those settings are still in the user's hand. The user can control where we need accuracy and where we do not need accuracy. So that is there. So you now know about the different industrial spices, and let me show you some areas where these industrial spice will be needed. This industrial spice are advanced softwares, right? And at the bottom, you need to learn, again I am emphasizing, the spice language to troubleshoot any of the design errors, or any of the spice verification errors, or any of the mixed mode verification errors. So you have to equip yourself with the spice. That is the backbone. So you have to learn the spice language very good. Now let us see in the next slide where the spice is used in VLSI. We will talk about various domains where the spice is used nowadays. Currently, when you are watching the video, all these areas, the spice is used either in form of pure spice, or used in the form of accelerated spice, or in the form of fast spice. Let me point out the domains. First one is the analog design. We have talked and touched base this few slides back. The next one is the full custom design. We already have an episode about the full custom design. Go ahead and search this episode, and the link is also given in the description. From there, you can also go ahead and learn about the full custom and the semi-custom design. Next is the semi-custom design. So we have also talked in this, we have an entire episode, so I am not going in details. So please go ahead and watch these particular episodes from the link given in the description, or you can alternatively search in our FAQ playlist. I think there it will be. The next domain is memory characterization, and also we have an episode on the memory characterization. I think it has been linked with the open source tool called the Open RAM. So you will also find it in our channel. Don't worry, all the links of these things are given just to broaden your view about the VLSI industry where the spice is used. Next is the IP characterization. So we have another episode on the standard cell characterization, and there are other IPs which are also characterized electrically. Here we are talking about the Liberty, right? That is for the standard cell characterization. Liberty, it's an industry standard format. So Liberty is industry standard for the standard cell characterization. The next one is the EM analysis. We have another episode on the EM, and now we already have a marathon of it. We have statistical analysis, Monte Carlo. We have talked about few slides back, and these are needed for a large design where we are doing the statistical analysis of the circuit. Next one is the aging analysis. Aging analysis is used in the reliability analysis, even for a digital chip. For there, we use the aging models given by the foundry, and we use the spice simulations to calculate how many years our chip will need. So that is the aging analysis. The next one is the IR drop analysis. So we have episodes on IR drop, and also that is included in our latest marathon. So which includes these two. That means the EM and IR. Please go ahead and watch that marathon. The link is given in the description.
Next is the full chip analysis. The full chip analysis is nothing but the analysis of a design that is more on the side of the full custom or semi-customs. We have the episode on the full custom and semi-custom, so you can watch that to understand about the full chip, right? Full chip analysis is nothing but simulating the whole chip together using the spice. Obviously not with the pure spice, because that will take maybe months, rather than using the fast spice and the accelerate spice wherever which one is applicable. Next one is the analog verification. Analog verification happens very frequently for the analog IP design. There we verify the functionality of the analog block that we have designed. And next is the analog and mixed mode verification. So this is very much used in multiple analog mixed signal IP. That is the, we give one example here, like the USB, right? USB is IP, right? So that uses the analog mixed signal verification. And you can also have SerDes. Nowadays, the SerDes is very much popular. That also uses the analog mixed signal verification. That means to test its functionality, we need to simulate the analog and the digital simulations together. And there are special simulators for that. Don't worry, you will get familiar once you enter the industry. So we are done talking about the need of the spice in various sectors in the VLSI arena. Now you know why you have to learn the spice, because not only one particular area, multiple areas need spice skills. And again, I am saying, even with an advanced tool like accelerated spice or the first spice, still at the bottom, the spice language is used, and you have to troubleshoot any of your error using the spice language. So there is the backbone, that is the spice language that you have to learn. Software will do its functionality, but the error and troubleshooting, that is the responsibility of a design and verification engineer or the verification engineer for the analog signal part or the analog part, will have to be done in an efficient manner. And for that, you have to learn the spice, as well as you have to learn well the Verilog and the Verilog A. So we have already covered the Verilog and the Verilog A in this channel. Now we are covering the spice. So you are getting ready. If you learn these three things, you are getting for this particular domain where the mixed mode analysis and mixed mode design, that is the analog mixed signal, that is done in VLSI. So let us move on to the next slide to see what is the analog and mixed signal design and verification is, where from we are talking so much about this, right? So here in this slide, we'll talk about the analog and mixed signal design and verification. First, the simulation method. Digital portion modeled with Verilog or VHDL, and with the Verilog AMS and VHDL AMS, we design the analog part. The analog portion model in spice also. So it could be a complex combination of Verilog and then Verilog AMS and spice, or Verilog and spice. There could be multiple permutation and combinations of analog and mixed signal design and verification. Like I have given two examples like SerDes and the USB. These two uses the mixed mode design and verification architecture, right? Signals passed to and fro between the Verilog and the spice models for interaction of the simulation. Now the simulators are also equipped to interpret this particular boundary, and if it is Verilog and Verilog A, right, for that also we have some connectors in between that are defined in the language. Verilog A or the Verilog AMS, I have talked in the Verilog A series about these things at the last. So you can go ahead and watch that marathon if you want to know and you are inquisitive about these things. Purpose. What is the purpose of the analog mixed signal design and verification? Model and simulate digital and analog components for accurate system level simulation. So that means some blocks will perform in analog way and some blocks will perform in digital way. However, when the chip is performing, that means the actual silicon chip, the entire operation has to be sum of the two. That means we have to sum of the analog behavior and the digital behavior and the handshake between them. That is the purpose of doing an analog mixed mode design and verification. Allows early detection and correction of design issues. This will be the main goal and the main responsibility of the engineer who is doing either the design or the verification in the mixed mode area, that is the analog mixed signal area. Applications. Useful for mixed signal circuits like microcontrollers with ADCs or signal processing with digital interfaces. So these are some examples where it is applicable, right? Valuable for verifying functionality before fabrication, because this is a mixed mode, right? If we fabricate the entire thing in a wrong fashion and the outputs are coming wrong, after fabrication, lot of silicon wafers are wasted and huge money is lost. So we have to save the money from being lost, and hence we have to do this mixed mode design and verification in advance. The next point is common in signal processing, data acquisition and control system. So these are some areas you should also have a look by your inquisitive mind. Now comes the benefits. What are the benefits of this analog mixed signal design and verification that exist in today's VLSI industry? Enables accurate system level simulations. So the accuracy is achieved. We are doing the analog part separately and the Verilog part separately, and then we having the handshaking in between. So there could be multiple combination, as I have said, like the Verilog, Verilog A and the Verilog and the Spice, or it is Verilog AMS. So there could be multiple combinations and permutations. Facilitates early detection and correction of design issues. That means the error may come from the design. We can predict it. So the predictability is in our hand, and we are saving money for the company, and we are able to design a very correct chip in the analog mixed signal domain. Essential for application requiring both analog and digital processing. So this is the need, because this is the view with which we are designing the mixed mode designs. That means the mixed signal design. Signal means whatever sending from one area, and mixed mode means the mode of designing. That means we are using the analog and digital things side by side. So we are done here talking about the analog and the mixed mode design and verification. So let us move on to the next slide. Here we will go quick slide for frequent interrelation and interaction of SPICE with different areas. Now let us see what are those areas. Here is SPICE, and it is used to interact with different file formats or domains like schematic. So schematic design is something that is performed using the schematic design tool. One example for the free tool is the LT Spice, where we design it with the schematics and then we can run SPICE simulation. So SPICE is at the bottom. Next one is Verilog A. So we might have a design where both the Verilog A and the SPICE is used. So it's a mixed mode design. The DSPF file. This is a parasitic extraction file. Specifically, it is used for the IP blocks. And here the entire extraction is done in a SPICE compatible manner. That means whatever parasitics are extracted along with the subcircuit that are present, all those data is there. You can go and check in the internet about this DSPF, and we already have an episode on SPEF in the STA series. It is very much close to the SPEF, but there is some difference. The difference is it is SPICE ready, where the SPEF is not SPICE ready. So the DSPF file that can be used as just to include the post layout effects into the SPICE simulation. Next one is SPF, which is, you can say, this one is another format, generally comes as the output of the extraction tool. Next one is CDL. So CDL is another file format which is related to the schematic, right? Where the schematic design is performed and saved into CDL. Next one is BSIM. So now the model for the MOSFETs that are part of the CMOS is coded into the BSIM, and in the Verilog A series or in the marathon, you can go ahead in, I think, first couple of slides. You will find very much detail about this BSIM. So please refer to that, and we will not repeat many things. So the basic models of the CMOS, that is the different MOSFETs that comes from the foundry, is in the BSIM format. Earlier these things were in the SPICE, nowadays they are in the Verilog A. So all those details and data are there in the Verilog A series, or you can directly go to the Verilog A marathon. We are done here. So we have SPICE and the different things which are related to SPICE in terms of software or file formats we have talked about here. Now let us move on to the next slide. So here we will talk about the common SPICE syntax file extensions. So there are several SPICE file extensions for separate EDA tools in the industry, or you may come across them outside the industry where you are using it for your classroom practice. So all are there. So don't get confused. All of them will have the SPICE in their tummy. So let us get familiar with the formats. The CIR file, right? The extension is CIR, however, the description is in the SPICE language. For tool to tool, there will be some different variations or some different things. If you take a tk-diff, you can find out the difference between two tools saving the CIR. So if you use the tool A from EDA vendor A and tool B from the EDA vendor B, right? So they both can have output of CIR. And this is true, right, for other file format. So there will be some difference. Not the fundamental difference, but software specific difference. And I cannot give you much more detail about this. Only you can see this once you are inside the VLSI industry. Next one is the SP. The .sp is another popular file format for the SPICE files. So SPICE, you can see abbreviated as SP, and CIR is abbreviation of the circuit. Another one is called the MDL. Now MDL is the model, is the abbreviation of the model. The spice model I am talking about, right? It could be coming from the foundry, which at the bottom it may have some missing related data. So that file will be in MDL. But however, this MDL is a part of the spice syntax. The file extension is different. However, the formats used inside this comes from the spice definition. The next one is CKT. So CKT could be another form of the spice file. Some tools may support this extension. You get familiar, the circuit, the CIR means circuit and CKT means also circuit. PSP means spice. So there could be multiple extensions for tool to tool. There could be multiple extension from one tool to another tool. Next is the SCS. So SCS is another kind of file format that is used in the industry, and the internal data, that is the inside the tummy of the SCS file, there will be spice syntax. These are all for your knowledge purpose. Next comes the .lib. The .lib we will go through in this series, right? The .lib is the library of the models. That is another file format. It is not the characterization .lib. It is the .lib in the spice. It is very much different. The .lib that we have talked about in the STA series, that .lib is different and this .lib is different. Although the extensions both are .lib. Now the .lib is the library of the collection of the models coming from the foundry. So this is the .lib for spice, and .lib for STA is completely different. So don't get confused. So when you are having a .lib, open it and check it whether it is for spice or whether it is for the static timing analysis. In both cases, the formats are different. In this series, we will cover this particular .lib, and we have already covered the .lib that is applicable for STA in the STA series. So in case you want to clear your vision, you can compare the both episodes. So in upcoming episodes, we will go in detail of this .lib in this spice, and that will be relevant and specific to spice. So we are done here. Let's move on to the next slide. Thank you very much for watching up to this point, and don't forget to like, share and subscribe. In case you have some dislikes, put that as in words in the comment section down below, and bye for today.